Hello and welcome to this lecture of the course Elements of Mechanical Vibrations. In the previous lecture, we discussed the response to harmonic excitation wherein the force amplitude was constant one, and in today's lecture we will discuss how the response to a rotating unbalance is obtained, particularly because in rotating unbalance case the amplitude of the excitation force is going to change with the rotational speed. And in the later part of the lecture, we will discuss how the response is obtained when the damping is not viscous damping, but is a structural or a Coulomb kind of a damping. Okay. So, till now the excitation force f of t has been usually written as some constant amplitude e to the power j omega t, and we I think discussed couple of times that this f naught is assumed to be constant irrespective of the excitation frequency omega, but we all know that whenever we account for the excitation due to the unbalance which is rotating with the shaft, so the amplitude of that excitation force, which is typically written as m e omega square e to the power j omega t. So, this amplitude itself is a function of or is dependent on the square of the frequency or the rotational frequency of the shaft. So, it means that the assumption with which we have drawn the amplification curve that f naught is constant is really not valid. So, we will discuss as to what changes because of the fact that the amplitude of excitation force is a function of frequency, and therefore, it is not going to be constant value throughout the excitation frequency range. Okay. So, this is obvious. So, let us look at how the response would look like and the amplitude of response can be obtained. So, obviously, if this is the case, then you go by the same process as we have followed all the time, that on the right hand side the excitation force is now going to be explicitly written as m e omega square. Usually I prefer writing this as u omega square e to the power j omega t, where u is the unbalance, and in practice people refer unbalance as u, which is the product of the unbalanced mass times the eccentricity at which the unbalanced mass is located. So, for example, this would be epsilon, the position of the unbalanced mass m from the axis of rotation. So, this m multiplied by epsilon, that product itself is unbalanced, and there is a reason, practical reason why it is usually clubbed together as a product, and it is called unbalance. So, the unbalance has a unit of kg meter as the product of mass and the eccentricity epsilon. In practice, the unit is more commonly kg millimeter. So, the eccentricity is in millimeters and the mass is in kg, but for the sake of this mathematical analysis, let us keep that for the sake of consistency with the units. Let us assume that this u represents the unbalance, which is mass times eccentricity. Now, here you must be very careful in understanding that this mass is the mass which is offset from the center of rotation, and epsilon is the location of that offset mass with respect to the axis of rotation. So, usually it gets a bit of misinterpreted as the mass of the system. So, let us be clear that this mass can be any value, not necessarily the mass of the system. Although it is true that for the sake of convenience, we say that the entire mass of this rotor is offset at a distance of epsilon, then things become little more easier and simpler to work with. So, in any case, by assuming the unbalance to be u, and then we solve this by the usual process of assuming the response, and because this is going to be solved for a constant rotational speed, that means we are going to still consider the rotational speed to be constant. So, for that constant rotational speed, the assumption of the vibration response, let us say x of t as we assume, equal to capital X e to the power j omega t, that is still valid because we are considering a constant rotational speed of the rotor. Now, this structure as such could be investigated as a torsional vibratory system, as a lateral vibrate or a bending vibration system, or vertically longitudinal vibration system. In any case, this unbalanced force can either generate a vertical translatory or vertical harmonic force, or it can generate a harmonic torsional excitation, or it can generate a harmonic moment, and so on. So, whichever way you model this vibratory system, the excitation still is harmonic, and thus the process of investigation is still the same. So, with the assumption of the response as this, we can substitute this assumed response in the governing equation of motion, and it is possible to show that this capital X, when you substitute into this left hand side part, would again be coming out to be k minus m omega square plus j c omega into x, x I am taking constant, plus you will obviously have e to the power j omega t as a common factor just like x, and then on the right hand side you will have u omega square e to the power j omega t. Okay. So, the way we did it for the for a simple vibratory system, single degree of freedom system with constant force amplitude, the same process will apply, and it is just as straightforward to show that finally, this amplitude x, keeping on the left hand side all terms taken on the right, and some mathematical manipulation which we have already done, this is what you will finally get as the amplitude of vibratory response in terms of the unbalance u and the excitation frequency omega. Obviously, we are not accounting for the transient part of the total response, that we have discussed a number of times why it is typically neglected or ignored. So, steady state vibratory response amplitude capital X is given by this expression, and that is typically how the rotating unbalance excitation generates vibratory response capital X. Now, what we shall do is we can take this mass we can take this k out of this particular expression and take it in the numerator, and it is possible to write this numerator as u omega square. So, I will divide this by omega n square just to bring it into our common notation as you see here, and that basically means that this is similar to or is equal to u times I will keep that omega, this is to be multiplied by omega n square to keep it the same. So, I am multiplying and dividing it by omega n square, and so this gives us u omega u r square. So, let me rub this off, make sure that we are on the same page here. So, multiplying and dividing it by omega n square. So, this term now changes to what? Omega upon omega n whole square is u r square, okay, and omega n square is what? K over m. Now, when we take k out from here, this entire expression is a familiar expression in the square root sign, which is this, and when the k is taken to the numerator, this cancels out with this k which is taken out, and you will find that u over m in the numerator. So, this numerator will now change to u r square over m divided by square root of 1 minus r square whole square plus 2 zeta r whole square. So, it is left to you as an exercise to figure it out whether this is correct or not, right. And this capital X, I can now take capital X over u upon m. Okay. Why am I doing that? Because the unit of u over m is distance, right. So, it is in distance units, because u is kg meters. Okay. So, it is a product of mass and eccentricity. So, that makes this response dimensionless or normalized with respect to the constant quantity which is u over m, assuming that the unbalance is constant, and of course, the mass is as well. So, you are left with what? R square upon square root of 1 minus r square whole square plus 2 zeta r whole square. That is our usual expression, except for the fact that in the numerator instead of 1 you have r square, okay. And in the left hand side, this particular term is again a dimensionless response, or I can call this as a normalized vibratory response, normalized with respect to u over m. Okay. Now, this u over m is, if we call this as x g, then x over x g, which is the same as this, is your dynamic magnifier, or sort of a scaled frequency response function h omega. So, that ratio is this quantity, which now can be plotted so as to see what kind of a response we get from by plotting this as a function of the frequency ratio. Now, frequency ratio r, which is omega over omega n, is actually the rotational speed. Okay. It is the normalized rotational speed, or a dimensionless rotational speed, because this is changing with the rotational, I mean this is representing the rotational frequency, and this is the natural frequency of the system. So, when we plot it with respect to r, we are essentially plotting how the response changes as the speed of rotation increases. Okay. So, this is one thing, and then let us also look at what alternate things that we can discuss here. X upon epsilon. So, now in this case u over m is also epsilon actually. So, this u over m x g is actually the unbalanced eccentricity provided. Now, this is very important, that is sometimes can be a confusing thing, is that this x over epsilon, okay, this x over epsilon is actually what we have done is this u over m, which is there in the denominator. I am basically replacing the unbalanced u by mass times the eccentricity at which the mass is located, divided by m. But important to note that this m is actually the system mass, it is the mass of the vibratory system. So, in practice what we typically get by a measurement process is the total product. Okay. When you experimentally find the unbalance in a typical rotor system, you won't be, I mean you do not really get mass separated and eccentricity separated, you get basically the total unbalance in the system. Now, if we assume that the total rotor mass is offset with the distance eccentricity epsilon, then the unbalance, sorry, the epsilon, the eccentricity would be obtained by dividing the unbalance that you get by the mass of the system or mass of the rotor. So, if you do that, this u over m is essentially the unbalanced eccentricity. Okay. So, x over epsilon is equal to this expression, provided that you are talking about this epsilon as the one which you obtain by offsetting the entire mass of the rotor from the rotational axis. Okay. Sometimes if you have found out this unbalance, I might use a larger epsilon and put a balancing mass of a smaller value than this m, which is the system's or rotor's mass. Okay. So, the unbalance here is the product of the mass times eccentricity, and assuming that eccentricity epsilon corresponds to the total mass. We divide it, and that way the ratio x over x g, or this ratio that we have got basically reduces to capital X upon epsilon. Okay. So, now with this amplitude ratio x over epsilon, you can find out the response amplitude normalized with respect to the unbalanced eccentricity as a function of frequency. So, if I plot this, let me rub this off now. So, if I plot this ratio now as a function of frequency ratio, I get the variation as seen here. So, either you can call this as x over x g, or it could be x over epsilon. Okay. So, as expected, if the frequency of rotation is 0, okay, then the numerator will be 0, and so it starts, the response variation starts with 0 at 0 rotational speed, which is expected physically. There is no excitation frequency, there will be no response. So, capital X is 0, and then as the speed of rotation increases, again it passes through the resonance, and then the value of x over epsilon changes with the speed. On just like what we expected, there will be large resonant vibrations at the frequency of rotation omega equal to undamped natural frequency. Now, damping plays its own role, the way it has done for the previous case of constant force amplitude also, that it sort of reduces the resonant amplitude as the damping value increases. So, corresponding to theoretically infinite amplitude at undamped case or damping equal to 0, there is a limiting amplitude as the damping factor increases, and as you can see that the amplitude at resonance can be significantly reduced by choosing an appropriate level of damping. The only couple of things that are required to be noticed here, and is important to distinguish the results of rotating unbalanced case vis-a-vis results with constant excitation amplitude case. Okay. Is that if you notice here, the peak amplitude with damping increasing is shifted towards right compared to the case when for a constant excitation amplitude it was shifted towards the left, if you remember. Okay. This same graph, if you remember, when was plotted for x over 0 frequency deflection, the dynamic magnifier actually started from the value of 1, and let us say this was for damping equal to 0.1. For the low level of for a higher level of damping, the peak actually shifts towards left. So, let us say if this is zeta equal to 0.3, right, and the peak is observed at a frequency omega p. Okay. So, if you are plotting this with as a frequency and not frequency ratio, then this is undamped natural frequency. So, I mean it will be slightly on the left hand side of the undamped natural frequency. So, this peak frequency, do you recall what was the expression for this peak frequency for the case of constant amplitude excitation force? If you remember, this is square root of 1 minus 2 zeta square. So, if the zeta is 0, this omega p will be at undamped natural frequency as expected, but as zeta increases it will slightly reduced. So, the frequency at which the peak is observed reduces for the case of constant excitation force amplitude, whereas in this case we are observing obviously that the peak omega p here, now I can write this as a ratio of omega p over omega n, that that frequency ratio is shifting on the right hand side, and this omega p in the case of rotating unbalance case is given by omega n over square root of 1 minus 2 zeta square, and it is possible to find this out again by following the same process. You remember what we did? We took a derivative of this ratio with respect to r, equated it to 0, figured out what that expression r is. You will find that that expression of r in the case of rotating unbalance would turn out to be r equal to 1 over square root of 1 minus 2 zeta square. Okay. That is the speed ratio at which you will get the peak amplitude. And again, for the same way we did it earlier, you can find out the quality factor for this case also. Okay. So, and there also you will find that the quality factor still remains 1 upon 2 zeta. So, quality factor in case of rotating unbalance case is no different than for the case of constant amplitude excitation, constant amplitude force harmonic excitation. So, the quality factors remains the same. So, all your methods of finding out the damping in the system using measurement data will still be valid, even if the curve starts from 0 and passes through the resonance. And so, there is one more interesting difference here, that for the constant amplitude excitation, okay, for the constant amplitude excitation, as the frequency ratio increases, your response becomes smaller. Okay. So, x over xst means that this ratio will approach a very low value as the speed increases to a very large value, whereas you are seeing here that this response ratio is approaching what? Is approaching a value of 1. And what does that signify? That at very large rotational speed, this amplitude of response x over epsilon will approach a value of 1, which actually means that the amplitude will approach a value of eccentricity. Okay. So, if you spin faster and faster, your amplitudes will obviously not be as large as they are at resonance, but they will approach a value of unbalanced eccentricity. Now, that is very interesting, because as the speed increases, if it approaches eccentricity value, to reduce the value of x itself, vibration amplitude, our objective is to have a less or a small vibration amplitude. What do? You reduce the unbalanced eccentricity. It is like reducing the unbalance itself, u equal to m times epsilon. So, you cannot change mass. Okay. So, if you sort of try to reduce this epsilon value, you eventually will reduce x. Now, what is the process of reducing epsilon? Unbalanced eccentricity is to balance the rotor, right? That is, practically we do. Practically, we try and balance the rotor by reducing the offset, or reducing the offset of mass center from the geometric center or the rotational axis. And so, therefore, physically balancing method will eventually try to minimize epsilon to a very, very small value, which eventually leads to a reduced amplitude of vibration, which is expected here. So, practically you can expect reducing unbalanced eccentricity is reducing the response. Mathematically, what is epsilon? It is the amplitude of, or a magnitude of your unbalanced excitation force, okay, f of t. When you reduce epsilon, you are essentially reducing the excitation force itself. So, when there is a minimum force exciting the system, there will be obviously minimum response, right, of course away from the resonance. And of course, even otherwise this x is going to be dependent on the magnitude of your excitation force. So, by reducing or minimizing the unbalanced eccentricity, mathematically you try to minimize the source of your vibration. Practically it is like reducing the value of response x by reducing the unbalanced eccentricity. So, this is all about the rotating unbalance case as a natural extension to the case of constant amplitude harmonic excitation case, right. Okay, now, if we try to look that in a slightly different way, which means that we actually physically look at how a rotor behaves, which is most of the 99 plus times of the case is basically going to have a rotating disc where the unbalance can be assumed to be located. The shaft is assumed to have very little unbalance as such, and with certain assumptions as a simplistic first cut analysis, what we assume is that the rotor is nothing but a shaft with a disc in the center of the span. That is what this type of a rotor is called in practice. So, a rotor with a massless shaft, the shaft will obviously not be massless, but compared to the disc mass, if it is slender shaft, the mass will be much smaller, right. And therefore, we assume a massless elastic shaft. It is our assumption. So, all the strain energy is stored in the shaft, right, as it deflects it, and the disc is assumed rigid. So, it does not flex as such and has all the mass. Okay. So, this is an assumption that with that assumption we can carry out the preliminary response analysis, and that kind of a rotor very simplistic model is called as a Jeffcott rotor in practice, and these bearings provide hinge support or a pinned support. So, this is simulating simply supported end condition. The rotor will have some unbalance, as you notice here, located at the eccentricity epsilon from the rotational axis. Please make a note here. This epsilon is not measured from here, it is measured from the axis of the shaft or the center of the disc. And so, what will happen is that the force will act from the axis of the shaft, and it will act through the eccentricity, the unbalance represented as G here. So, the force is going to act like that, and it is going to pull the shaft away from the bearing axis. So, this is our bearing axis. So, as the rotor spins with certain speed, the centrifugal force because of unbalance is going to act on the axis of the shaft or the spinning shaft, and then it is going to pull that shaft outwards in the direction of the force, and the position of the disc center or the shaft center in the plane where the disc is located in this particular plane. So, if you consider this as the plane perpendicular to the axis of the bearing axis and containing the disc, then obviously the position of this disc center is given by the radial distance r. Okay. So, the position vector of the center of the disc and of course, the center of the shaft at that location is given by r. Okay. Now, if I want to model this as a vibratory system, again I need a mass, the spring and a dashpot. So, I am going to work with a simple single degree of freedom equivalent of this physical shaft disc bearing system. Now, what is going to be representing the stiffness here? What is going to represent the damping, and what is going to represent the mass? Now, we have already declared that the shaft is massless, the disc is having all the mass. So, m here represents the disc and its mass, right. we are already declared that this is providing simple support. So, there is no stiffness in the bearings is infinitely rigid, it is only restricting the lateral motion in the two directions of the shaft. So, K is actually the stiffness of this elastic shaft. Okay. You can find out quantify this K by using your standard strength of material expressions. So, simply supported rotor or a simply supported beam with a center force, that 48 EI by L cube is going to be your stiffness K. Okay. What is going to be the damping? There is no, you do not see any dash pot here. So, damping C can be now an equivalent damping coming from the structural damping of the shaft material, because it is the shaft which is flexing. So, it is going to store all the strain energy, and then because of the intermolecular friction there will be dissipation of the vibratory energy. So, C equivalent will represent kind of a equivalent viscous damping proportional to the energy dissipated during the cyclic stretching of the shaft cross section. Now, this mass is what? It is basically we typically say that x dot and x double dot, x is the degree of freedom. Now, in this case we are going to work with because the disc is going to rotate like this. So, I can imagine that this shaft is or shaft center is going to move as the rotor spins, and it is going to move up, and then it is going to actually whirl around the bearing axis. So, the displacement or the vibratory motion can be considered in these two directions, horizontal and vertical. So, I can have x as well as the displacements along x as well as y. And where this mass is located, is this mass located here? Is the disc mass located at the shaft axis? So, what we are saying is unbalance is mass times eccentricity, and this mass, let us say, is assumed as the mass of the entire disc, and although it is exaggerated here, shown in a very highly exaggerated way, in actual disc which is mounted on the shaft, the offset of this mass center is very small. Okay. The amount of offset that you have, the shift of the mass center from the geometric center of rotation or axis of rotation is going to be very small. Okay. So, this is shown quite exaggerated here, but if that is the location of the mass, should we not take the acceleration of that mass center, isn't it? Because it is not this point which is going to have the the application of the Newton's second law will apply to the mass center and not the geometric center of rotation. Yeah, so there are two ways. One is you assume that the disc rotates about this axis, and then you assume some amount of unbalance. You can quantify this u value, which is the product of mass and eccentricity, or you can assume that this product is composed of the mass of the disc and eccentricity can be calculated from that. Okay. That is number one. Number two, you can assume that the way we have done in the previous slide, that there is a force which is going to be computed based on this unbalance, times omega square and so on. And then this acts like an external excitation to the disc. What we are going to do is, we are not going to explicitly assume that unbalanced excitation force. We are going to work our way by assuming that application of this free body diagram, considering the position of the mass center here. You will quickly realize that in a while. So, suppose we position, or you find out what is the displacement and acceleration at this g position, the mass center position. It is the position vector is representing is represented by ug and vg, in the two directions that we have assumed, x and y, the two orthogonal horizontal and vertical axis. So, the position of the mass center is given by ug and vg, whereas u and v is the position of the disk center, not the mass center. Okay. Okay, now, if you look at this same plot from the sideways, this is how it looks. If you look at the shaft from the bearing axis looking from the right hand side, the position of the shaft center is u and v in the two directions x and y, and the position of the mass center is ug and vg. Now, if we consider this disc as a free body with the mass located here, mx double dot in general, as our second law gets applied, is mass times the acceleration is all the forces acting, okay, in the direction of acceleration. So, now if we assume the displacements and accelerations you know the way we have done all the time in the past, let us say this is ug and ug double dot, right. So, that is basically the displacement and acceleration. Now, if we do that, this is how the governing equation of motion will turn out. Why? Because mass is equal to what? Now, what are the forces which are going to act? So, we are talking about the acceleration of the mass center, right, but is the disc getting restored to its bearing axis position by the can we write this as minus k times ug and the dissipating force as minus c times ug dot? You remember we have written mx double dot equal to minus kx minus cx dot, right. These are the restoring forces, the restoring force and the dissipating force, they are acting opposite to the direction of the motion, the x as well as x double dot. Now, why this is not correct? Because what is getting flexed is this point getting flexed? It is the shaft center which is getting flexed, right. Come back to this point. What will get restored? Because of the stretching in the shaft, the shaft center is going to get restored, okay. And similarly, this disc is moving. So, suppose you just imagine that this disc is moving in a fluid, okay. This disc is moving and whirling in the fluid. What will be the dissipating force? Dissipating force will be with respect to the center of rotation, okay. So, therefore, we really do not care where the mass center is. Mass center was required to be known for inertia, okay. And so, therefore, in this particular case k into ug is going to be incorrect. It has to be the displacement and velocities of the shaft center and not the mass center. So, this has to be u and this has to be u dot. What is ug? ug is what? U plus, so this u plus this value. Well, how much is that? The shaft has moved by an angle of omega t in time t, right. This is spinning with a rotational speed of omega, right. So, u plus what? Epsilon cos omega t, isn't it? Minus k into u minus c into u dot. Now, if you simplify this and then if you rearrange, this is what you will get in both the two directions, u as well as v. This is what you will, but you can notice that either ways you expect to get the same expression. So, even if you consider the mass to be located here and account for this shift in the mass center from the geometric rotational axis by replacing that by a force explicitly, right, you expect to get the same expression. This is another more classical way of getting the same expression for a rotor vibratory system at least. So, then what you do is you have two governing equations of motion. I will combine them by using a complex variable R w, which is this, and that is basically u plus j v, and when you substitute this complex response variable, I can multiply the second equation by j or I multiply the second equation and I will add the second equation to the first equation. So, this equation plus j into this equation and then using R w equal to u plus I v or j v, I will get this particular expression. So, you can combine them using complex notations, and that basically is a single governing equation of motion, quite similar to what we have started with in the earlier case. R w is just indicating that it is a whirl radius. Now, this motion of the shaft center around the bearing axis in the rotor vibration terminology is called as the whirl motion. It whirls around the bearing axis, and that whirl motion is nothing but a combined horizontal and vertical vibration of the rotor. Okay. So, when the shaft spins, that spinning motion is not vibration, that is a rigid body rotation about its own axis, but that stretched shaft when it rotates and when orbits around the bearing axis, that motion, whirl motion, is the vibration. Okay. Spinning is different, vibration is the whirl motion, and you can show that it is nothing but combined vertical and horizontal vibrations together will trace out a whirl orbit about the bearing axis, which is here. Is that clear? Now, the way we have done solution is very straightforward. We have done it umpteen number of times. We assume a harmonic response, and not only that, harmonic response with the same frequency as the spinning frequency. Why that is so? Because the unbalance is going to excite the system at the speed of rotation, and therefore, assuming a response with the amplitude capital R, e to the power j omega t minus phi is our assumed response, which is valid most of the times, okay, because most of the times the rotor is going to whirl with the same frequency as the rotational frequency or rotational speed, because unbalance is what we have considered. The excitation force here is unbalance. So, with this assumed vibration response of the rotor, we substitute this R w into this equation by getting an expression for R w dot, R w double dot, and then substituting them and solving as we have done number of times, you will ultimately get the response amplitude. This is similar to your capital X, okay, and on the right hand side you have m omega square epsilon over square root of k minus m omega square whole square plus c square omega square. Now, that again when you simplify, you will get the same expression as we have got. So, that is basically r over epsilon, that is what we got, r square upon the denominator, right. So, this is like dimensionless response, non-dimensionalized or normalized with respect to the eccentricity epsilon. Now, big epsilon or the unbalanced eccentricity for a given rotor is not going to change with rotation or with speed, right. For a given rotor bearing system, unless the unbalance changes for some reason, epsilon is going to be a constant value. So, you are normalizing capital R with respect to the unbalanced eccentricity, and the expression that we got here is similar to what we discussed couple of slides back. Okay. And of course, the angle phi. Now, what is angle phi here? Look at that, the figure that I have. Angle phi is typically what it represents is the phase between the response and a force. excitation force. In case of a spinning rotor, what is the excitation force? Unbalance. Okay. What is this? What is the response? That response vector is what? With respect to the bearing axis, this is our rotor vibration response, because it is the shaft that is whirling. Okay. So, the shaft center position is where we get the response, and obviously the response lags the force by an angle phi. So, the force will go first, will reach its value, peak value first, and the response will follow. Okay. That is what we have here as details of a rotor vibration case. Phi is the phase with which the response lags the excitation force. Now, this is very similar. In the past we have discussed how the forces are acting at different speeds of rotation. So, what you see, supposing we look at the range of speeds close to the resonance or critical speed. By the way, this resonance in a rotor bearing system is usually referred as a critical speed. That is the speed of rotation, which is the excitation frequency. When it is close to the natural frequency, then you have resonant vibration amplitudes. Now, if it operates close to resonance or close to critical speed, we know that when we plot this angle phi with respect to the rotational frequency ratio, that is omega over omega n, okay, the amplitude changes the way we have discussed already, the phase angle changes like this. So, this is corresponding to damping equal to 0, and this is for some higher level damping. Maybe I can say that this is probably 0. Maybe 1, this is 0.5, 4 or 3, and so on, right. As we know that it passes through 90 degrees irrespective of the damping value at the speed of rotation equal to undamped natural frequency. So, irrespective of damping, all the curves pass through this point, which is pi by 2, 90 degrees phase difference between force and the response. Okay. So, if it is operating close to resonance, this is how it shows up, like this is the response. Okay. So, this is the direction of your response. Where will the force be located? It is going to be acting on the shaft in the direction of the unbalance, right. So, this is your force and this is your response. Now, if it operates in a speed range lower than the critical, that means it is going to operate somewhere here. You may notice that now for this range of operation less than the critical, typically the angles are going to be, or the phase angles are going to be less than 40-45 degree. Usual angles are less than 30 degrees here, because the damping is typically small enough. So, but the point is, if it operates in the subcritical region, subcritical meaning that the speed of rotation omega is less than omega n, that is what this shaded area is representing at a particular speed of rotation. Now, when it operates there, then what happens? We have discussed in the previous slide that the force and the response, they have an acute angle between them. So, this is capital X and this is your force. So, the angle here is going to be phi, which is which is an acute angle. That's how it shows up. And so, what happens that if your rotor is spinning and whirling, so as the shaft center whirls around the bearing axis, the mass center will be located outside of this circle, and the shaft is going to be lying here, and the mass will be flipped outside of that rotation and outside of that whirl circle. Now, if on the contrary, if you operate post critical speed, that means you are operating at speeds more than resonance, maybe somewhere here, any speed more than the critical speed, the phase is now going to be an obtuse, because you can see that at any speed irrespective of damping, the angle is more than say 150 or so. So, it is close to 180 degrees as the damping reduces. So, typically this angle phi for the case of operation post critical is going to be such that the mass center will flip inside. So, if the shaft whirls like with this distance or this response amplitude, the mass is flipped inside, and theoretically at large speeds of operation this angle approaches 180 degrees. So, theoretically if the damping is 0, it actually coincides with this response vector, and so the force and response, they are almost opposite phase. Okay. And then for very large angles close to 180 degrees, it so happens that this G actually approaches a response R. You remember that for R approaching large values, what was x over epsilon? That approaches 1. Okay. Now, x in this case is basically your R, okay, or capital R is the amplitude, and so R will approach what? Epsilon, which is what we are seeing here because of that flipping and that angle being close to 180 degrees. The mass center actually comes close to the bearing axis. So, what happens is that the rotor is actually whirling with the mass center close to the bearing axis, and so you basically have the entire vibration whirl motion with an amplitude close to unbalanced eccentricity. And it actually so turns out that if you try to reduce eccentricity value, your response amplitude becomes 0 or close to 0. Okay. And that is basically the practical significance or a physical understanding of the phase angle. So, usually phase angle we ignore, there is just an expression that basically explains some of the interesting phenomena here, or the understanding of the vibration phenomena. Okay. So, as we discussed, below first critical speed, the whirl or the shaft whirls with this path. Okay. Again, very exaggerated view. In fact, this amplitude is going to be much smaller compared to the diameter of the shaft in fact, but just for the sake of illustration here, it shows that if it is operating below first critical speed, the mass center is outside of this. When it whirls beyond the first critical, beyond the critical, the mass center is flipped inside, and that is how it whirls. Okay. Maybe I can show you this animation how that motion is going to be. So, as it goes from this point, okay, and comes back to this point, as it moves from this point to start with and then comes back to this point, you must notice that this shaft has spun by one full rotation. So, 360 degrees. So, 360 degrees of this whirl motion, and same is the 360 degrees of its own spin motion, okay, will simultaneously happen. That is what typically called in practice of rotor vibration as a synchronous whirl. Okay. Synchronous whirl meaning it is synchronous to the speed of rotation or a spin motion. But again, let me remind you that it is this whirl amplitude that is vibration, and the spin motion is the rigid body rotation of the shaft about its own axis. All right. So, this is how it looks like. Now, what will happen for a motion at supercritical, that means beyond critical, that this particular point is going to be located all the time inside, and that is how it is going to spin like that.
In this animation, phase difference is 0.
Yeah, in this animation the phase difference is 0, just to illustrate how it works, but you can have some small phase lag or phase difference, but the point is if you start with this as the position of the unbalance, when it comes back here it will be at the same location. Okay. The one spin motion, one rotation about its own axis and one full rotation about the bearing axis happens with the same time period, that is synchronously moving and that. Okay, so having now discussed the basic philosophy of a sensor design, we discussed the seismometer and accelerometer. A slight introduction to finding the response to a harmonic excitation with Coulomb damping. We have always assumed that the damping is viscous damping. So, mx double dot plus cx dot plus kx equal to f of t is what we have all the time presumed, right. But in reality Coulomb damping is in fact more commonly expected to be present in a structure. So, we need to look at how you can evaluate the response if there is a Coulomb damping. But as we know and discussed, in case of a free vibration response to dry friction damping or Coulomb damping, that the response is not, the governing equation themselves are not linear, because the sign of the dissipating force keeps on flipping during a single oscillation cycle. So, it is strictly not a linear governing equation of motion, but we now make an assumption that if the dry friction force is small compared to the applied force F naught, then we can say that instead of that response being bilinear, like in one half oscillation it follows one governing equation, another half cycle another governing equation, but if these amplitudes of the friction force is small, the entire cycle here can be assumed to be close to harmonic, nearly harmonic. Okay. So, with this slight assumption in mind, which is expected to work well for getting an approximate response, we all know that the energy dissipated in a cycle for a purely viscous damping is given by this expression. You remember this, pi c omega x square is the energy dissipated in a cycle of oscillation. Okay. So, this of course is a structural damping case, and this is what we know that force versus the response curve looks like, and this area we have derived that the area is pi c omega x square. Now, in case of a friction damping or a Coulomb damping, what happens, this the same graph. So, this is for a pure viscous damping case, this is for material damping, and for a dry friction case we know that it is a rectangle like this, where this value is mu n and this is capital X, that amplitude of oscillation. So, this delta omega is going to be what for a friction damping case, 4 times mu n into x, is not it. So, when we want to now somehow equate this area under the curve for one cycle, and if you want to make use of the same equations that we have derived, now we have derived so many response equations assuming a viscous damping case. Now, what we are going to say is that we can treat the governing equations the same, except that the damping quantification of the damping as an equivalent viscous damping can happen by equating these two areas. So, we will keep using the same equations, but with a different value of C, okay. And then the solution becomes simpler and you do not invoke too much of an error in the estimation. We are not interested in finding out whether the response is, let us say 1.32957 like this. Even if we get the response to be this much is good enough for us, slight variation is okay. So, for all practical purposes, getting an equivalent damping by equating the energy dissipated in a cycle, irrespective of what is the mechanism, underlying mechanism, should suffice in getting an approximate response value. So, what we do is you equate these delta W for both the cases and then get an expression for an equivalent viscous damping even if the damping is not viscous. So, you may equate that area which you can find experimentally from a material damping or from a friction damping case. Now, when C equivalent is obtained like this, obviously the damping factor equivalent can be obtained in the same way. Okay. So, you know that Cc is 2 m omega n, and by using that you can get a zeta equivalent, and when you substitute this zeta equivalent in an expression for capital X, which we know is f naught over k square root of again 1 minus r square whole square plus 2 zeta r whole square. Now, in this case zeta is going to be zeta equivalent. Okay. When you substitute for this zeta equivalent in this equation, this is what you are expected to get. The response amplitude will be now in terms of the coefficient of friction, and capital N of course is going to be the normal reaction, which in general depending upon the situation would be the weight of the mass. Okay. Right. So, this is the way we can take care of Coulomb damping case by finding out an equivalent viscous damping factor. What happens if the forced vibration response is to be obtained for hysteretic damping? So, you have a mass and the structural damping is defined as combination of stiffness and damping. We discussed that it can be both stiffness and damping property in one single structural element, that is the engine mount or any rubber isolator, polymeric isolator, or even a simple structure, let us say an I beam or whatever is the material. So, the only problem or the only difference in this case we have discussed this, that it has a complex stiffness. You remember K was actually a complex stiffness. So, what is our governing equation of motion? Mx double dot plus this part, please revise and revisit all the discussion we had regarding the hysteretic or a structural damping case for free vibration conditions, and we have that time derived that it actually turns out to be a complex stiffness times the response x, and now it is going to be f e to the power j omega t. Okay. Now, here again, as long as the system is linear, we assume that the solution is going to be this x e to the power j omega t is the assumed solution, right. So, you assume the harmonic response, and now when you substitute that into this equation, what do you get? Minus omega square capital X m plus what is the complex stiffness expression, you remember? I am going to take e to the power j omega t out, and that is what I get here. Yeah, you remember what is the expression for the complex stiffness? It is K, the stiffness of the material. Okay. So, if I am trying to get that for a simple beam with a end mass here, and this beam is made of steel with certain cross section, then this beam has its own stiffness, the lateral stiffness, right, and the damping property is captured through a parameter called as what? Loss factor, yeah, structural damping coefficient 1 plus j into beta. You remember this was the complex stiffness that we derived when we discussed this first time in the free vibration case. So, please revisit that part. beta was what? Alpha over pi k. Okay. Beta is the loss factor, structural damping factor. Alpha is the constant of proportionality when we said that delta W is proportional to square of the amplitude. You remember delta W in a structural damping case was proportional to the square of the amplitude, and alpha was taken as the proportionality constant. So, this alpha is appearing here. So, this is what the complex stiffness is in terms of in the case of a structural damping or a material damping or a hysteretic damping. Now, with this in place, obviously I can write this as k 1 plus j beta minus m omega square, and capital X I am going to take out, and that is going to be equal to f. So, it basically gives me capital X, the response amplitude for a force harmonic force f e to the power j omega t as equal to f, and then I can take k out from, or let me keep it as it is to start with. So, it is basically k into 1 plus j into beta minus m omega square, and so if I take k out from the denominator and take it in the numerator here, I get what? 1 minus, you can show that, I leave it to you to figure this out, it is very straightforward and simple, plus j into beta. And we know that this is what? Dynamic magnifier yeah 1 minus r square whole square. No, this is going to be only 1 minus r square, not whole square. I am sorry for this. It is going to be only 1 minus r square. Okay, and then plus j beta. Now, this you can reorganize this again. I do not need to tell you how to reorganize this. This can be done by what you know very well, and then it is going to finally look like square root of 1 minus r square whole square plus j beta square. Sorry, I think all right. X over xst, the dynamic magnifier for a structural damping or a material damping or a hysteretic damping case. Okay. They mean the same. What is the expression for viscous damping? Okay. Quite a good similarity between the two. Now, what is the range or frequency region which is of most importance where the damping plays its role significantly? Near resonance. So, that is the case where R is close to 1. So, when R is close to 1, both responses are identical. Both responses, I mean for the structural damping and viscous damping, are identical for beta equal to 2 zeta. right. Yep. So, if you plot this frequency response for a viscous damping case and then a structural damping case, you would find that both of them have the same value at resonance, and at resonance beta is actually equal to 2 times the equivalent viscous damping, I mean the viscous damping coefficient. So, the parameter wise there is this relationship between the two, the loss factor and the viscous damping factor. Okay. And then of course, once this expression is known and you somehow through tests figure out what is the structural damping coefficient or a loss factor, you can substitute for this particular parameter in this equation to find out the response at any frequency of excitation, right. So, broadly the two expressions are quite similar in that sense. So, this is the summary of this lecture. Going beyond a typical constant amplitude harmonic excitation, we investigated and explored how the response to a rotating unbalanced case is obtained. In particular, how the whirl amplitude of the rotating shaft is obtained, what is the phase relationship between the forcing function and the response, and later the response to an alternate kind of damping such as Coulomb or structural damping have been obtained. These are the recall questions, couple of questions that you can attempt now based on the topics of the lecture, and the answers obviously will follow next.